All right, so let me share my screen. So we're gonna start out with some homework problems for right? This is homework number 1. And number 20. Of course, your numbers might be a bit different because I think it's randomized, but the nature of the problem will be exactly the same. So you had your matrix, the matrix that you're speaking of is 3, -2, 2, -5, 1, -3, -1, 8, and -2, -3, 2, 2, like this, right?
Yeah, Professor.
Okay. And then you said you couldn't put it in row reduced echelon form.
Yeah, like I tried a bunch of methods and I thought I got it to row reduced echelon form, but I think I tried like 3 times and all of them were wrong.
Okay, so first of all, what does row reduced echelon form consist of?
Zeros have to be on top and below of the pivot variables.
Right, the pivots, right? So where the pivots, right? You have pivots and there's zeros above and below the pivots, right? So zeros are above and below pivots. And the pivots consist of what? The leading ones, right? So it could be the fact that the pivots, the most that you can have are the number of rows. So if you have 3 rows, the most number of pivots you can have are 3. You can't have more than that because there's only 3 rows. And the ones have to appear like this. If it's possible, it may not be possible, but that's one thing, right? So I want to make all of these. Okay. And so what did you try to do?
When at like the first move, I think I did R1 plus R2 to try getting the pivot variable to be at the top left corner.
R1 plus R2 goes to
Sorry. R1 plus R3.
R1 plus R3. Oh, okay. But you know what you could have done a little easier? You could have just switched R1 and R2.
Oh, like completely switch them?
Right. Like R1 and R2, just switch them. Why? Because then it becomes 1, -3, -1, 8. And already look, boom, I got my pivot. You see that? So that move is kind of underrated because it's not utilized so much, but it's still a move. It's one of the elementary row operations. So boom, I got it. And this is a little bit easier now because now I can get rid of the 3 really quickly. I could get rid of the -2 really quickly. I could have done this. I could have divided this whole row by 3 and I would have had a 1. But then the moment you do that, um you introduce fractions into it, which I think it might work out eventually, but it's a lot more cumbersome. And now eliminating these numbers underneath should be a little bit easier, right? Because then you can do what? You can do negative R1 plus R2 goes into negative R3, -3 R1 plus R2 goes into R2, and then positive 2 R1 plus R3 goes into R3. So I'm getting rid of this guy and this guy at once. So that's going to be hopefully not too bad, right? So we got 1, -3, -1, 8. And then this becomes 0. -3 times -3 is positive 9 minus 2 is 7. -3 times -1 is -3 times -1 is positive 4 plus 2 is 6. And then -3 times 20 simply is -24 minus 5 is -29. That's what I got for the second row. And then the third row, I double 1 and this becomes 0. I double -3 minus 3 is still going to be -3. And then I double -1 and this becomes 0. And then I double 8 and I get 16 plus 2 is 18. So that's what I get. And then what? And then what can I do from here?
Could you do R2 plus 2R3 to try getting, actually no, you could try doing R1 minus R3 to try getting another 0 in the first row.
So say that one more time.
So R1 minus R3, so you get the -3 and then it'd be plus -3, which would end up being 0.
So you're trying to get rid of this 0?
Yeah,
So the thing is, once I establish this pivot, I'm good with this, right? I'm good with these here.
yeah.
Now the next pivot that I anticipate would have to be here. The problem is that if I do what you just said, right? If I use
Mhm.
row 1 to get rid of this -3, which is what you would expect, right? Because you want to make this a 0, correct?
Yeah.
But the problem is if I do that, I'm not going to leave these as zeros anymore. So like if I multiply this by -1, right? To make this a +3, and then I add this to this row, and this becomes a 0.
Hmm.
I multiply this whole row by -1, and this becomes -1.
Oh, okay.
So I no longer have a leading 1 anymore. I have this thing. So I'm going backwards. So,
Okay, gotcha.
yeah. So from here, this is where I kind of want to, like, either I can switch the rows, but yeah, it's not so pretty here because the 3 and the 7, they're not multiples of one another. So there's gonna be some kind of fractions involved in um this one here. I just want to make sure that I got all of the I just got all the numbers correct. Did I get all the numbers correct in the beginning? Everything's okay, right? The negative signs and all that.
Yeah.
That should be right. So let me just see if yeah, this looks okay. -3, -3, -3. Yeah, this looks right. So sometimes the computations are like these annoying little things where the signs can, mess up here and there. You can forget and it's negative or it should be positive. So you have to be careful with those things. But okay, so far so good. Then the best thing I would do is, I guess you can just stick with this for now and then just say you got negative, not negative. You reduce the second row. So you have 1, -3, -1, 8, and then you got 0, and then you got 1, and you got 6/7, and then you got -29/7. So this looks kind of weird. And I got 0, -3, 0, and 18. So then I have the two pivots so far. I got two pivots that appear.
Oh, wait, Professor, for the to get the pivot in the middle, can you do R2 would be R2 plus 2R3, like, and the result would be R2?
Oh, yeah. So you say you want to double this row and
Yeah,
then you add it to this one.
yeah.
Let's see. Yeah, I think that might actually be a little nicer. Let me see. Yeah, so let's see if that works out because this is already, so we got, so I'm gonna change this, right? So this would be positive. So you double R3, you add that to R2, and then you make that new row. So this becomes 1. This becomes 6, right? Because you're multiplying this by 2, which is just by itself, and then you multiply 18 by, yeah, I like this way. And then you multiply 18 by 2, you get 36. So this becomes -29. This becomes +7. This is -3, and this is 18. Yeah, I like that way a lot better because I don't have to worry about the fractions. That's perfectly fine. So, okay, now I have that. And then I want to get rid of that. I want to get rid of what? I want to get rid of this guy, right? So then I got to get rid of that -3 beneath the 1. So what do? I need to multiply this by 3, the second row by 3, and add that to the third row and make that my new third row. So when I do that, I get 1, -3, -1, 8. I get 0, 1, 6, 7, and this becomes 0. This becomes 0. And then this becomes what? 3 times 6 is 18, plus 0 is 18. And then I get 3 times 7 is 21. And then this becomes 39, right? Did I do that right? 39, right? So something went awry though. Hold on. 3 times 1, yeah, 3 times 2, 6. 6 is okay. Actually, wait, I think I did something. There's something a mistake here, right? Somewhere. 3 times 36. I may have done something. But now looking back at this, instead of, I like your way too. I do like it. But I think what we should have done is swap these rows, because 3 and 18, they're, I can divide by 3 and make, and I don't have to worry about the fractions. So this is what I would do just to make sure everything. So like I would do this instead. I would switch row 2 with row 3. Row 2 switch with row 3. So then I would have -3, 0, 18, and then this would be 7, 6, -29. Then I would divide by a third, row 2, make that my new row. And so this becomes 0. No, this becomes 1. This becomes 0, and this becomes -6. This is 7, 6, -29. And then I would say -7 R2, when I add that to R3, gives me a new row R3. This becomes 1, 0, 0, -3, 1, 0. This is 0, 6. And then this becomes -1, 8, -6. And then this becomes 42 minus 29 is what? 13. Is that correct? So there seems to be something's up with this. Is there a miscalculation somewhere? Let me see something. So, okay, for those of you who need, so what? Let me help you guys out with something here. Hold on, let me see the chat. Could you do multiple operations in one step so you don't have to keep on rewriting the whole matrix over and over? Of course. Of course, you can do everything at once. That's the goal. You can just do all at once, and eventually you don't have to do this every single time, every single like. But it's just to give you guys for now insight as to what every step is. If I do all steps into one single step at once, then you won't see what just happened. You just be like magic, basically. Yeah. So James says, I think you should redo. Okay, before we do any redo, I just want to help you guys out with 2R1 plus R3 is wrong. 2R1 plus R3. That could be wrong. I double it. So see, it's little things like this. So if I double R1, this becomes 0, right? If I double this, You're right. You're right. Thank you. Thank you, Ken. I appreciate that. You see, I made one little tiny mistake, guys. When you double, when you double -3, you get -6. If you add it to -3, you don't get -3. What's wrong with me? What do you get? You get -9. So that was that one. You see that? One little thing made everything just garbage, right? So then I'm gonna do this. I'm gonna switch. I'm still gonna switch the R2 and the R3, but this will not be a -3. This will be a -9 instead. And I'm not gonna divide by 3. I'm gonna divide by a -9th, right? And so this becomes the correct answer, which is -2. And then I'm gonna multiply this still by 7. And this will no longer be -6. This would be 2. This would be 0. This would be 6. And then what do you get? Hold on. So this is hold on. -2. This is -14. +14, pardon me. So this is +14. Wait a minute. Becomes +14 minus 29, right? So this becomes -15. Is so this is correct. The second row is right, but then this third row is a little bit weird. Did I do something wrong with? Is there anything else that I did incorrect? I feel like I may have done something, one little thing, right? Because -29 looks a little strange. So 2 times 6 is 8. Yeah, it's 18. This is okay. And then -3R1. And then maybe I did this one wrong too. This part here. -3, this becomes 0. A -3, 7, that's right. And then -3, this is my God, guys, what's wrong with me? So -3 times -1 is +3 plus 2 is not 6. What is it? Isn't it 5? So this is just like little tedious mistakes. And then -3, -20. So this should be right. -29 should be right. So then when you switch this should be 5, right? Okay, now we're talking, right? Now we're talking, right, guys? So this becomes 5. Okay, I'm not crazy. I'm not crazy. All right. Thanks, guys. So I appreciate it. So then look what we have. We got 1, and then this 5 here. Look, what does that become? We get 1/5 R3 goes into R3. This becomes 1, -3, -1, 8. I get 0, 1, 0, -2. This becomes 0, 0, 1, -3. So what did I have? What do I have this in? This is in row row echelon form. It's not row reduced echelon form yet because these zeros here, I don't have zeros yet, but I have ones here in the diagonal where the pivots are, and I got zeros all underneath. So this is an RR, this is an REF. And I have to do a few more things, right? I need to get rid of this -1. And how do I get rid of that -1? You do R3 plus R1 goes into R1. So this becomes 1, -3, -0. And then this becomes 5. This is 0, 1, 0, -2, 0, 0, 1, -3. And then one last thing. Now I have to do what? What do I have to do to get rid of that last entry above here? I just need to do what? Triple R2 and then add that to R1. and make that my new R1. And then when I do that, I get 1, 0, 0, 0, 1, 0, 0, 0, 1. This is -3. This is -2. And if I multiply this by 3, I get -6 plus 5 is -1. So this should be the RREF. So be careful, be very mindful. This is very like tedious sometimes, right? To keep the numbers right. Like there's a lot of things that go like moving parts here. And as long as you're consistent with the steps and you're able to, do a good bookkeeping here, and be careful with adding and multiplying numbers, which sometimes, we just gloss over, we mess up. Like, I don't know. I think with the 6, I was thinking 3 times 2 instead of -3, instead of 3 plus 2. You see? So things like that, little things that may not seem like a big deal can be a big deal as you go on. So be careful with that. But yeah, this should be it. And I don't think it's going to be anything crazy, right? It's just very straightforward. Apply the row reduce, apply the row operations to get it to row reduce echelon form. So does that help? Does that make sense? Seeing it live in person, seeing how things can go awry and then seeing how you can get back into the swing of things. Okay, anything else? Anything else? But yeah, so what I wanted to show you with this one as well is that if you have a graphing calculator, the TI-80, a TI-84 plus, I can show you how to do this on the calculator itself. Question 4, yeah, I'll get to question 4. Let me just share it with you. So if you have a TI-84 plus, something like this, so you can actually do this in one fell swoop. You go to math. No, pardon me. You go to second X, like you go to where it says matrix. So you go second and you press this button here. And so all of these are matrices. Hold on, let me go back. So you can edit them. So let me edit matrix A. Remember we use capital letters to denote matrices. So let me press A, and then remember the first number represents the number of rows and the second number represents the number of columns. So in this problem, we have 3 by 4. So automatically, boom, I get a matrix and I can just fill in the numbers the way we did by hand. So the first row is 3, then it's -2, pardon me. So we got -2, then we have 2, then we have -5, then we have 1, then we got -3. So this is a good way when you have to do this by hand. It's a good way to just check that you did your work correct. So this is more of a check. And then you get -2, and then you get -3, and then you get 2. Whoops. And then you have 2 again. So this is my matrix A, right? I got the same matrix that I just used. I just plugged in the numbers in the correct entries, the rows, and the columns. So then how do we do this? What do we do after we have that? We go to second matrix again, and then we go to math. Look at all these things that you're going to eventually know all about this stuff. You're going to know about the determinants. You're going to know about transpose, the dimension, identity. You're going to know all about this. And there's 2 things here, you see? You have REF and you have RREF. So let's see what they give us for REF. So if I do REF, whoops, shouldn't be here. I should be in the main page. So go again to second matrix and then go math, then go to REF. So the REF, and then we're going to use second matrix A. So when we close parentheses, what do we get? So remember what I told you, REF is not a unique, there's different row echelon forms of a matrix. It's not always the same. And so this is my REF this matrix. You can't really see, I guess, let me just see. Yeah, you can't really see the rest of it. But now let me try the row reduced echelon form. So I do second matrix, and I go to math, and I go to RREF instead. And then I choose my matrix A, and I press enter. And I get exactly what I was supposed to get. I get the exact matrix. So this is an excellent way, if you have a calculator like this, to check your work when you have to actually do it by hand. So this is a great way to check. Okay, so your calculator can do all of these things, of course, immediately, but we had to take a little bit more time. Okay, so that's the last question. Okay, number 4 actually is exactly what we left off on from last class, which was on matrix multiplication. Okay, so I can kind of kill 2 birds with 1 stone here. Let me share my screen here. So number 4, numbers can be different. Your numbers can be different than mine. Okay, so it says the vector, my vector says the vector -17, -10, and 9, right, is a linear combination, right, of what? Of the vectors. I'm going to talk about vectors too. -4, 5, -5, and 9, -6, 6. Okay, and it says if and only if the matrix equation AX has a solution. So, okay. And then it says what is A, right? I want to know what A, they want to know what A is, and they want to know what B is. So they have this A here, and they want to know what B is. So they want to know what to fill in here, basically. So we have 3 spaces here, and we have 6 spaces here, right? So first of all, let's talk about this. Linear combinations. And to know about linear combinations, we're gonna continue with this idea of matrix multiplication for now. Remember we talked about matrix multiplication, so recall. Recall matrix multiplication and how we defined it. It was a very particular way, wasn't it? So like an example, if I have 2, 3, 5, 1, and I multiply this by -1, 2, 1, 0, 2, for example, right? How do I get my product? Does anybody remember how we get the product and we multiply 2 matrices together? What was the rule behind matrix multiplication?
Was it like 2 times -1, 2 times 1, and then 3 times, I mean plus 3 times 0, 3 times 2?
Well, remember, it's kind of like this. You get row 1, you get column 1, right? So you get the first row of the first matrix multiplied by the first column of the second matrix. And then you do what's called a dot product. So you take row 1, you perform dot product of row 1 and column 1 of matrix 1, and this is matrix 2. It's like a weird operation, but it's 2 times -1 plus 5 times 1. This is 2, -2 plus 5, which is 3. This is my entry 3. And I'm gonna do the exact same thing for the next row or the next entry. Row 2 is what? Row 2 is the entry in the second row and the first column of the product is the dot product of the row 2 in the first matrix multiplied by the first column in the second matrix. So this becomes what? 3 times -1 is -3 plus 1 times 1, which is -3 plus 1 is -2, and then so on and so forth. Then in the next entry, right, which is row 1, column 2, I get row 1, column 2, and I multiply 2 with 0, which is 0, plus 5 times 2, which is 10. And then this becomes what? The last entry is row 2, column 2. So I get second row of the first matrix multiplied in dot product fashion with the second column. So 3 times 0 is 0 plus 1 times 2, which is 2. So this is my result. I just want to make sure, does everybody see how we multiply things out? So how do I write this out in a general sense? So what's the general rule for matrix multiplication? So if I want to find A times B, right? This is my rule, A times B, and I want to find the ith, jth entry. So remember, I represents the number, the row number, and J represents the column number. So if I have my product AB, which would be this, right? AB, if this is A and this is B, this would be A times B. If I want to find the ith, jth entry, then what do I have to do? And this is where things get a little bit interesting because we're going to use summation notation for this. So I'm going to do this. I'm going to take the ith row of the ith row of the first matrix, which is A, right? A is the first matrix, B is the second matrix. So the ith row, to get the ith, jth entry of the matrix, I get the ith row of the first matrix, whatever that ith row is. It could be the first row, second row, third row. And then I get the ith row, and then I take this. I do this. This is the notation. And K goes from 1 through 1 through K. No, 1 through N. Actually, let me call this M. Now, this looks a little strange, right? But the idea is this. The idea is that if A is a n by m matrix, so this is n by m. So this is A1, 1, A1, 2, all the way to A 1, m. And this is A2, 1, all the way down to AN1. And this goes all the way to ANM, right? So we have m rows and m columns. When you multiply this to B, what's B going to be? So there's a huge condition. There's a huge condition in order for matrix multiplication to actually be possible. So remember when we added matrices or subtracted matrices, the condition was that the sizes of both matrices have to be exactly the same. So the condition for multiplying matrices, they don't have to necessarily have the same size. But they do have to have is that the number of columns of left matrix, so the one on the left, which is the first one, this has to equal the number of rows in right matrix, or the second matrix. This is the first matrix. So let me shift this stuff down. So do you see that the matrices, the sizes don't have to necessarily match up, but the number of columns of this guy, so I have 2 columns here, has to match up with the rows here, because then the operation wouldn't be possible if that weren't true. So this is very important actually. So then hopefully this will make a bit more sense, because if I have a B matrix that I'm multiplying, the number of rows in my second matrix has to be equal to the number of columns in my first matrix. So this would be M by P matrix, for example. Then this would be what? This would be A1, 1, A1, 2, all the way down to A1P. This is A2, 1, all the way down to AM1. This goes all the way to A1, pardon me, AMP. So again, I'm generalizing this now. I'm generalizing this. So I have a matrix that has a size of n by m, right? N rows, m columns. The matrix that I'm multiplying by has m rows and p columns. So then when I multiply A times B, for example, right? And I want to know what the entry is, right? If I want to know what the entry is for the, oh, sorry, pardon me. This all should be B's, or not A's. Pardon me. This should be B's, because I'm using the B matrix. So for example, if I want to know what this guy is here, if I want to know what a B I J is, right? If I want to, sorry, 1 1. If I want to know what the first entry of this product is, what do I have to do? What is A B 1 1 gonna be? Of course, AB is just the name of the product AB, A times B. So what do I have to do? I have to take the first row of the first column, and I have to multiply it in this very particular way with the first column of the second matrix. What does that look like? It looks like A11 times B11 plus A12 times B21 plus A13 times B31 dot, and you get the point, right? It goes all the way to what? A1M multiplied by BM1. So this entire thing, when you perform the operation, goes in here. And you repeat the process. So instead of writing it all out this way, what do we do? What do we do instead? We generalize this, right? We generalize it for the ith entry, the entry in the ith row and in the jth column. So this is the entry of matrix AB in row I and column J. So given this example here, what's going to happen? I'm going to have this. I'm going to have I1, B1, B1I. Sorry, yeah. B1, let me see, 1I. And then this becomes plus AI2, B2I plus AI3, B3I. And I go all the way down to oh, pardon me, this should be J, not I. All these are J's. Because this is the jth, the B's come from the jth column and the A's come from the ith row. So this is B3J, and this goes all the way to BI M, and this is BMJ. So instead of writing this all out this way, I'm going to shorthand notation this. I'm going to write this as the summation of A, I, and I'm gonna have a new index called K. K is what's being that's what's changing. And B, K, J. And K runs from 1. You see this? The K's here goes from 1 all the way to M. And that's why this is the rule for multiplication of a general set of matrices. So if I have two matrices and I want to multiply them, the condition first is that the number of columns of the first, which is at the left side of the matrix, the left matrix, has to equal the number of rows of the second matrix or of the right matrix. Because if they're equal, when they're equal, you can create this kind of what's called dot product, which is defined this way. You take the first component of the first row and then the first component of the first of the column. And then you pair them up. So the only way that's possible, the only way you can pair these entries up is if they have the same number in them. That's why they have to have the number of columns here has to equal the number of rows here. So you can pair them up, you pairwise multiply them, and then you add them up. That's what the dot product is. It's a pairwise, it's a component-wise multiplication, way of adding a multiplication, a product. So that's why this gets kind of, messy a bit in a way with all these indices, because I'm generalizing this for the ith, jth term of a random, I guess you can say, a pair of matrices where the rows of one equals the columns of the other. Can you specify which matrix can only be multiplied with one the same size and which can be multiplied with number of column equals number of rows? Can you ask that question in another way? What do you mean by that? Can you specify which matrix can only? I don't necessarily understand what you mean by can only be multiplied with the one with the same size. So what I told you was that you don't need to multiply matrices with the same size necessarily. If you have the same size matrices, they are going to be multiplied. How about if you multiply matrix is 3 by 1, the second matrix 1 by 3? Yes. Yes. So let's do that, right? Let's do an example of a 3 by 1 matrix. So what's a 3 by 1 matrix? Call this A. You can make this up. 3 by 1 means what? 3 rows, 1 column. So literally it's like this: 2, 3, 4, for example. And let's look at the second matrix, which is 1 by 3, which is what? Let's do 1, 0, negative 1. Okay. And then we're going to multiply A by B. So this is going to be a what? A 2, 3, 4. And I'm dot product. I'm multiplying this with 1, 0, negative 1. So we can literally go through the rule here. So first of all, these match up, don't they? The number of columns in A is 1, and the number of rows in B is 1. So these match, right? So then we can perform we can do that as well. But we can perform matrix multiplication. And there's one little thing that I forgot to mention, is that what is the size of the product? What is the size of the product of AB? So one little thing, very important thing though. So what do you guys think? What's going to be the size when you multiply A by B? The outside dimensions crossed, right? Do you guys see that? So you're going to have how many rows in AB? Yep, you're going to have, right. So I'm doing this, right? This is going to be what? Column 1. And then how many times am I doing this? How many times am I doing this? I'm going to be doing this, the number of rows that I have in A. So my new matrix would have n rows of this. And then how many columns am I going to have? Well, how many columns do I have in bar B? So see, I'm taking the number of rows of this guy and I'm pairing them with the number of columns. So I'm performing this operation. I'm performing this operation n times m times p times, pardon me. Do you guys see that? That's why it's going to be an n by p matrix at the end. So the size, so as is one last thing here, the size of product is n by p in this example. But I just want you guys to understand why that is so. I got n rows in A and I got p columns in B. I'm performing this operation, matrix operation, with the rows of A with the columns of B. So if I'm performing this every single time, there's n of them, and I'm doing this with p columns. So the total number is n times p, n times p matrix entries. So the number of rows of A and the number of columns of B is my new matrix size. So in this case, the number of rows in A is 3 and the number of columns of B is 3. So the result would be a 3 by 3 matrix. So then what's the first entry? Can anybody tell me the first entry? The first row in the first column. So remember, you take the first row of the first matrix, the first column of the second matrix. But this becomes quite easy, doesn't it? It's just 2 times 1. It's 2. And then what? You can either go in this direction or you can go in this direction, or you can go in any direction really. But if you want to know the second entry here, the row 1, column 2, right? What does that mean? Row 1, column 2. This becomes what? 0. Right?
So
Right. And then you do the last entry in the first row. So row 1, column 3. Row 1, column 3. This is what? -2.
-2.
And then you just keep on doing this. Do you see the pattern now? This becomes what? 3 times 1, 3 times 0, 3 times -1. This is just multiplying this row here by 3. This is 3, 0, -3. And then so on and so forth. This is 4, 0, -4. So a 3 by 1 matrix multiplied by a 1 by 3 matrix produces a 3 by 3 matrix. And remember, the conditions must be met that the inner numbers dimensions have to be the same, and the product, the result, are the outer dimensions of each matrix. Would there be a question that the rows doesn't match the columns? If the number of rows don't match the number of columns of the second matrix, then you wouldn't be able to perform matrix multiplication. So I'm assuming if you have a question like that, it would probably be like a trick question. It would try to be like, oh, can you multiply these two matrices? Or then it would be like, oh, what would have to be the number of dimensions or the number of columns for one matrix in order to multiply these matrices? So something like that. But if you have just two matrices where the number of rows of the left one doesn't equal the number of rows of the right one, matrix multiplication it's impossible. It doesn't make any sense to do it. Okay, so this is matrix multiplication. Now, how is this related? How is this related to number 4, right? That's really what we're trying to get to. So let me just say one thing about this. Okay, so now I hope that makes sense, right? Multiplying matrices. I want to give you another example though before we, like, what happens when I do the opposite? What if I do a matrix that's 1 by 4? So I do like 1, 2, 3, 4. and I have a matrix that's 4 by 1. What if I switch it around? Or I'm gonna say, you know what? I'm gonna make this a little different. 4 by 2. What happens when I do that? So this is 1, 0, -2, 5, -3, 4, 1, 2. For example, what would this be? AB. So first of all, do the inner dimensions match up? They do, right? The number of columns in A equals the number of rows in B. So I can do that. And then what would be the dimension size of my new matrix? What's the number of rows of A with the number of columns in B? So this would be a 1 by 2 matrix. I already know what I'm supposed to get, right? I'm supposed to get just 2 numbers. So then what is that number? What are these entries? What do I have to put for this? Or how would I get it? Remember, row 1, this I only have 1 row, and then column 1. So row 1 is related to what? The first matrix, right? The left matrix. And I'm doing it with column 1. So I'm pairwise multiplying these entries and I'm adding them up. So then AB 1, 1 would be what? 1 times 1 plus 2 times 0 plus 3 times -2 plus 4 times 5. What is that? This is 1 plus 0 minus 6 plus 20, which is what? 1 plus 14, which is 15. So the first entry here is 15. And then AB 2, 2, I mean, sorry, 1, 2, because I only have 1 row and the second column. So this would be what? Row 1 times column 2, pairwise, of course, pairwise component, multiplying each entry with the corresponding entry. So this becomes 1 times -3 plus 2 times 4 plus 3 times 1 plus 4 times 2. Sorry, I wrote that too quickly. 1 times 3. So this is 3 plus 8 plus 3. So, oh, I meant to write 1 times -3. So this is -3 plus 8 plus 3 plus 8. The 3's cancel, and I'm left with 16. So that should be the result, right? So I multiplied a matrix that's 1 by 4 and a matrix by 4 by 2, and I got a 1 by 2 matrix at the end. And I did the what's called the dot product or pairwise multiplication, and I added up the pairs of those products. Does that make sense, guys? Multiplication, just the fact of multiplying matrices, how we multiply matrices, how the dimensions have to match up a certain way. Does everybody make sense with that? Any questions about that? We're good? Yes, no, maybe so. Can we do BA? So that's no?
Yeah.
Oh. So that's where I want to get to. That's what I want to get to, Chaitanya. Matrices, matrix multiplication. So one big thing, guys, note. Matrix multiplication is not what's called commutative. So this is a new kind of thing where, for example, A times B does not necessarily equal B times A. With numbers, right? 3 times 4 is 4 times 3. With numbers, we can multiply any order we want. With matrices, we care a lot about what the order of the matrix multiplication is. As you can tell, if I were to multiply the opposite way, if I were to do B times A here, would that work out? Well, this is a 4 by 2 matrix. This is a 1 by 4 matrix. I wouldn't be able to do this. This would not give me anything, right? This would not give me anything because these inner dimensions don't even match up. You have 2 rows for B and you have only 2 columns for B and you only have 1 row for A. This idea of multiplying it in the way we've been multiplying it is impossible. So no, BA is not possible in this case, and not necessarily possible. So that's one thing. Matrix multiplication is not commutative. It's not. Okay, so we're dealing with a different kind of object, mathematical object, not numbers anymore, but matrices. Now, I want to just make another recall of what we've been doing before, right? So recall, I forgot the first, I just want to bring up the first example we did. So x plus y equals 3, right? X plus y equals 3. And 2x plus 3y equals 8. I remember we did this problem. We already know how to do this problem, blah, 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 right? We already know. And then we solved it in more than one way. We use matrices, right? And we rewrote it as a matrix. We did 1, 1, 2, 3, and then we augmented it, right? 3, 8, right? This is what we did. An augmented matrix, right? But what I want to do now is try to show you how I can write this as a matrix equation. So I'm going to write this as a matrix equation. And now my matrix equation has this form. A, which is a matrix, X, we put a little bar over it, equals B. I mean, a little arrow over it. And these arrows we indicate to be what are called vectors. And we'll talk about what vectors are, right? But a vector is simply just a matrix. It's just matrices. Now, how can I write this as a matrix equation? Well, A is the coefficient matrix, right? We already know what the coefficient matrix is. And if you look at this, do you see this? This is 1 times x plus 1 times y. This is 2 times x plus 3 times y, right? And if I consider this as a matrix, do you see how I can break this up? Do you see how this looks like this? Really? 1, 2, 1, 3. And I'm multiplying this by a matrix of 2 by 1 size that has the entries x and y in them. Do you see that? And now this equals what? This equals 3, 8. Because this is what this is saying. Do you see how I'm able to break this down into a matrix A with a column equal to another column? So this here is my A, my matrix coefficient. This here is my variable vector, and this is my other vector, or 2 by 1 matrix. Do you guys see that? So I can now create matrix equations, single matrix equations for any system that I'm given. The first matrix is the coefficients. The second matrix, which is be considered a column vector, is the variables that we have, and then what we equal it are the numbers that each equation is equal to. So look at the other example that we had in lecture 2, I believe. So I had this, right? So then what would be the matrix equation for this? Well, I know if I have A minus 2B, so I multiply B by 2 or negative 2. I'm not sure about what. Oh, if you multiply, do you multiply B by 2 or negative 2? It's either or. Either you multiply by 2 and then you subtract A and B, or you multiply by negative 2 and you add A and B. Does that make sense, Chaitanya? So either or, it's okay. So this would be what? What would be the matrix equation for this? This would be what? 1, 1, 2, right? This is 2, 4, -3. This is 3, 6, -5. This would be, this is my A. And then what would be the column vector associated with that? It would be X, Y, Z. And when do you see that? When I perform matrix multiplication, I get exactly this. I get exactly what I have on the left. I get 1 times X plus 1 times Y plus 2 times Z. And then I get 2 times X plus 4 times Y minus 3 times Z. And then 3 times X plus 6 times Y minus 5 times Z. Do you see that? That pairing? And then this has to equal the vector. I should move this a little bit. Sorry about that. I should move this a little bit here so I don't have to like scrunch this up. This is equal to 9, 1, 0. So what's the idea? The idea is to figure out what is this here, right? That's eventually the goal of ours, is to figure out that missing thing, which is this column vector or this 3 by 1 matrix. Okay, so does everybody understand this, what I'm doing here? How I'm rewriting a system into a matrix equation using matrices and column vectors? Does that make sense? Okay, so if that's clear, and I'm still trying to, give you the backdrop for number 4, because once you have this, then number 4 becomes, I think, a little bit simpler. There's another way we can also think about the examples that we just had, right? So I can think about now, look, I can think about X plus Y equals 3, 2X plus Y equals 8. I can think about this as what we just wrote, right? As the matrix equation 1, 1, 2, 3, XY. And I can do one more thing to this. I can also think of this, if you see it, I can think of this as a matrix, X plus Y, 2X plus 3Y, right? That's when I multiply this out. When I multiply this out, this is what I get, right? I get a matrix like this. This equals 3, 8. Now you're like, wait, that doesn't, you just wrote it again. Why does this matter? Now, because there's a sum here, right? There's a sum, right? Can't I rewrite this as a sum of 2 matrices? Can't I write this as X, 2X plus Y, 3Y? Can't I do that? Yes, Baldwin?
I just have a quick question. Where did you get the 3 on the second row?
Oh, I think I just rewrote it. I wrote it incorrectly. Pardon me. This should be 2X plus 3Y. I was using the previous example again.
Oh,
Yeah,
okay,
yeah.
okay.
I'm just
Gotcha.
rewriting it again. But what I'm doing now
I'm
is
following.
I'm taking this guy and just writing it as if I'm actually performing the matrix multiplication. Like I'm actually doing 1 times X plus Y, right? That's what I'm going to get as my result,
Understood. I
right?
got it.
And then what happens after that? I'm able to do what? I'm able to rewrite it now as a sum of 2 matrices, which are 2 by 1 matrices, which are considered column vectors, because a vector is just one, like has one column. So now I have a sum of 2 different matrices, right? Or 2 column vectors. And then what else can I do now? What is X and Y? You consider them as scalars. So I can write this as what? X times 1, 2 plus Y times 1, 3. What am I trying to say? I'm trying to say this. Where did this come from? Where did this come from? This came from this. So 1, 1, 2, 3. When I multiply this by xy, I can think of it, the product, as a what's called a linear combination. This is called a linear combination of columns in a matrix. Why is it linear? And we're gonna be talking about this word a lot. Linear combinations. It's linear because I'm multiplying. There's nothing raised to a power other than 1. Everything is to the first power. That's why it's linear, first of all. And the combination, what that word combination entails is this multiplication and addition aspect. So linear combination is a sum of multiples of two things. And these two things are of things. And these things are the columns of the matrix. So when you multiply a matrix coefficient with a column vector, another way to interpret this is a linear combination of the column vectors. So it's like saying, how many of these do I need? How many of these columns do I need? And how many of this column do I need in order to create this number here? And then this is where it becomes something geometric. You can interpret this geometrically. And so that's why the vectors come into play. So we can think of this as the following. In two-dimensional space, right? One comma two. So this is so now I'm gonna talk about column vectors. One comma two, you can think of it as 1 comma 2. 1, 2, you can think of it as 1 comma 2. Where's 1 comma 2 here? 1, 2. A vector has a magnitude and a direction. So you draw a kind of like an arrow, 1 comma 2. So vectors have magnitude and direction. The magnitude is how long it is, and the direction is where it's point, like how long the arrow is, and the direction is where it points. So 1, 2 indicates that my column vector or my vector starts from the origin and it stretches forward to that point. And then what's the other vector? 1, 3. What's 1, 3 going to be? 1, 3 is going to be somewhere here, right? So this is my other vector. And then I want to say, what I want to figure out in a way, what I'm asking is how many of these vectors do I need? And in adding to how many vectors of 1, 3 do I need? 1, 3 and 1, 2 do I need to produce the vector 3, 8? 3, 8 will be somewhere here, right? 1, 3 and 8. It's a little bit not drawn to scale here. But this is the idea. The idea is how many of these do I need and these do I need? So when I add them up, I get this as a result. That's another interpretation of it. And yes, Baldwin, you have a question?
I had a question, but I guess it's kind of off topic, but how do you determine the angle of the vector? Or that
Wow.
doesn't matter.
Well, it depends on what you're trying to do. Of course, it definitely matters. For example, when you talk about polar coordinates, that may appear. So polar coordinates, of course. And how do you determine the angle, right? You want to determine the angle. Well, first you have to figure out what are you trying to find the angle in reference to. So normally, what do we decide to be 0 degrees? Don't we decide to be the x-axis to be 0 degrees? Someone just arbitrarily decided, hey, let's make this side here 0 degrees. So once we make that point of reference, then it's very simple. You can think of it as a right triangle. You can think of this as a right triangle where one of the sides Can't even make a right triangle. Where one of the sides is a 1, the other side is a 2. And I'm trying to, I know this is 90, and I'm trying to find this angle here.
Oh,
So then
gotcha.
this becomes what? This becomes tangent, right? Of theta is
Mhm.
2/1. So then what's theta? Theta is arctan of 2. So of course, and then you can generalize this to find the angle for any vector is the arctan of that, of the ratio of x of y over x. But for this class, you don't necessarily need to know that much. But when you talk about polar coordinates, then of course this appears all the time with the
Thank you.
vectors. Yeah, no problem. Okay, so this system, so see how we solve this problem, right? And we just found x and y and we said, oh, who cares? Now this has more of a geometric meaning. And what was our answer again? Wasn't it 1, 2? Right? Wasn't that the answer for x and y? If you got 1 plus 2 is 3, and then 2 plus 6 is 8, right? So my solution is 1, 2. Okay. So let me draw this out actually. Hold on, guys. And pardon me for my dog. He's just, if you hear him,
Yeah.
pardon me for that. So let me erase this. I just want to draw this out a little bit better. So I already know, I already know my solution here. X equals 1 and y equals 2. I already know this. So let me just draw this out again. So I know 1, 2, right? I know this is 1 and this is 2. So this is my first vector here. And then 1, 3, I have another one. And then 3, 8. 4, 5, 6, 7, 8. So what I just found out was that I need 1, 2, which is this one here. I need one of these. And then I need 2 of these guys. What does that mean? What does it mean to have 2 of them? That means I need to extend this vector. I need to put on top of it again. I need to put I need another vector here. So when I need another vector, I'm going to put another vector here. So these are 2 of them, right? These are 2 of vector 1, 3. And then I'm going to place this vector 1, 2 here. From here, I do 1, I go up. Is it 3? Let me see, 1, 2, right? So the idea is that it's supposed to like touch exactly. Oh, I just drew this completely. Drew this wrong, didn't I? Yeah, I drew this one wrong. Pardon me for that. I just drew this one completely wrong. 3, 8 is this. 3, 8 is right here. So maybe this is not the greatest example, but this is the idea. The idea is that I connect. Yeah, this is not a good example actually. The idea is that I connect 2 of these vectors together, and then I add one more, attach it to one more, so that the result is 3, 8. That's the geometric meaning behind this statement. That's the geometric meaning. And then when you do the 3 by 3 example, it's the same idea. You have a vector in 3-dimensional spaces, and you have 3 of them. And you want to know how many of each do I need, so that when I put them together and I add them up, I get the result, the vector at the end. So going back to number 4, which is the example that problem that really sparked this whole matrix multiplication thing. They're asking you, what is the linear combination of AB. So actually, this is pretty much done, isn't it? What would I have to fill in for this? I think I went way more in depth than I needed to do this problem.
I think the A matrix would just be, so the first column would be -4, 5, -5, and the second column would be 9, -6, 6, and then B would be -17, -10, and 9.
That's how you do number 4. That's it. So the idea was to understand first matrix multiplication. Once you understand matrix multiplication, you understand that how you can rewrite systems as a matrix equation. Once you understand matrix equations, then you understand that the result vector is really just a linear combination of the columns of A. And so they're telling you this is a linear combination of these two columns. So what you just put together is that, oh, these are the columns of my matrix A, and this is the result that I want. This vector here is the result that I want. And so therefore, the A matrix would be the columns that we have here, and the resulting vector, the column vector, would have to be the vector that we wanted.
That makes sense now.
That makes sense now, right?
Yeah.
I know. So some of these problems, when you see them at first, you're like, wait, what in the world? So you have to break down what the meaning is. You have to break down some operations, particularly matrix multiplication, which is essential. But then you realize they're not really overly trying to, grill you with understanding matrix multiplication. You just have to understand the connection between matrix multiplication and the linear combination of columns of a matrix.
If I know an end result of a matrix, can I find a linear combination of it or not really?
Wow, I think that's considered like that's an example of like an inverse problem where you're trying to figure out. The thing is, I think there's not a unique solution. Like if you know what your end result and you're trying to find a linear combination of it, of what the question is, you're trying to find a linear combination of what? What are those column vectors that you're considering? There's probably an infinite number of vectors that when you take a linear combination of it, give you the result.
Oh, right. That's how we can solve, like if A times some other matrix equals B, right? A times X, that X vector over there equals the B vector. I think it's A inverse times XYZ will equal XYZ in the B.
Right. But your question was saying if you have the end results, would I be able to figure out? I think that's what I interpreted.
Yeah.
Like, were you able to if I were just given this and I didn't have this, would I be able to figure out these two things? Is that what you're saying?
It is where I started, but now I see that I probably wouldn't be able to find that.
You wouldn't be able to.
But would I be able to find that X vector?
That's exactly the goal of this whole linear algebra portion of the semester. We're going to be concerned with knowing this, and figuring out this. That's essentially what we've been studying every time we solve a system of equations. That's exactly what we want. We want what x, y, z is. We want to know what x, y is, right? And now we're making that x, y, we're considering that as one unknown. It's a vector. It's one complete unknown. Of course, it has several entries, right? But that's one unknown. So excellent connection, right? Recall how we solve this. How do we solve 5x equals 3, for example? I want to know what x is, right? We divide by 5. And what happens? X equals 3/5, and we're done. We move on. We go, now we have quadratic equations, so on and so forth. But now look what we're doing here. We're doing A times X equals B. What's going to happen is I'm going to know this, like I know this, I'm gonna know this like I know this, but of course now we're dealing with different objects. We're not dealing with just single numbers anymore. We're dealing with a matrix of numbers. So I'm gonna know that this matrix of numbers, I'm gonna know this column vector, which is just a matrix with a single, right? A single column. But I won't know what this is. So then the immediate knee-jerk reaction would be like, oh, how do I figure out what this is? Oh, I'm gonna divide by A, right? That's the immediate knee-jerk reaction. So then what you would think is that, oh, X, the missing unknown is just the column vector divided by the matrix. But then the question becomes, how do you divide by matrices? And is that even feasible? Is that even feasible? We know how to add matrices. We know how to subtract matrices. Now we know how to multiply matrices. The question is division an operation that even makes sense with
And-
matrices? Because
and
it kind
multiply by
of
the
makes
inverse?
sense with, huh?
Multiply by the inverse, maybe?
Right.
But I don't know the inverse.
Right. So we'll talk about how to find the inverse, but that's the idea. The idea is, wait, in reality, when I did 5x equals 3, in reality, what I did was I multiplied by the multiplicative inverse of 5. I really did this, 5 to the negative 1 power, and I really multiplied this by 5 to the negative 1 power. And what happens when you multiply a number by its multiplicative inverse? The word multiplicative inverse implies you're undoing multiplication. And if you undo multiplication, what you're left with is what's something that's called the identity element, which is the number that's when you multiply by that thing gives you itself, right? So in this case, the multiplicative identity is 1, of course, because 5 times 1 is 1, you know? So that's the idea. The idea is that you multiply by multiplicative inverse so that you're cancel out the 5. But what does it mean to cancel out anything? You see these words we just use so commonly, and now we have to really put these words now and have a concrete meaning to them. When you cancel something, you're reducing it to the multiplicative identity. And this is when what's called abstract algebra emerges. This idea of what are called groups and rings. And so matrices create are the objects. If you consider all the matrices that ever exist together, they're considered a non-commutative ring. But we're not going to get into that part. But I'm just saying, if you ever do study, for those of you who will study, or any of you who are interested in studying abstract algebra, linear algebra is like an immediate thing that pops up. So yes, Chaitanya, you said if we have a linear combination of ax equals b, what does that mean? Can we add and do elimination? Add, I'm not sure about adding, but what we're gonna be doing now is, yeah, pardon me, we don't know the inverse, right? So yes, you're right. We can perform Gauss-Jordan elimination to the matrix A, augment it with column B, and then you figure out what X is. That's how we've been doing it. So we've essentially been already solving matrix equations utilizing elimination method. We have, but eventually we're not going to be doing that anymore. The elimination process, you start to see, it takes a long time. So then in reality, what we're going to be considering now, instead of doing dividing by, instead of dividing by A, we're going to be multiplying by the inverse of A. And because the order of the order of multiplication matters, we have to apply left multiplication of the inverse. So we're doing what's called left multiplication of inverse. And when we do that, we're also doing that to, if we do whatever we do on one side of the equation, we have to do it to the other. So we're actually be multiplying by the inverse of A on the left side of B. Now the question that arises is, what is A inverse multiplied by A equal? So think about it. 5 times the inverse multiplicative inverse of 5 gives me 1, right? And 1 is the multiplicative identity. So now the question becomes, if I multiply a matrix, and let's suppose this matrix does have an inverse, and in this idea of inverse, multiplicative inverse, when I multiply a matrix with its multiplicative inverse, I should get the multiplicative identity. That's what I should get, right? I should get what's called the multiplicative identity. Which in essence is like saying I get one. But the question is, what is one in the world of matrices? One matrix. So the idea is what we're going to speak about is what's called the identity matrix. This is called the identity matrix. And we're going to denote it with I. I will be the I matrix, not one. Yeah, it is. It is the I, not I-E-Y-E, but I as in I, the letter I, capital letter I. So the capital letter I is called the identity matrix. So when I multiply the inverse, a matrix with its inverse, I get the identity. And what is the identity? Does anybody know what the identity is? I think Mir tried to write it. So the identity is a matrix that has 1 in the diagonals and zeros everywhere else. That's the identity matrix. And you can try it yourself, right? Like you say, wait, is this really the identity? If it really is that the multiplicative identity, of course, this is multiplicative, not the additive identity. The additive identity would all be just zeros, but this is the multiplicative identity matrix. So like if I have 2, 3, 4, 5, right, and I want to multiply by the identity matrix or the identity, the identity element of matrices, then I would have to multiply it by this matrix. Now, what's the result that I should get? I should get back 2, 3, 4, 5. So the way we defined multiplication was, what would we do? First row, first column. 2 times 1 plus 3 times 0 will give me what? 2. And then first row, if I want to know the next entry in the row, first row, second column, 2 times 0 is 0 plus 3 times 1 is 3. Do you guys see that? Do you guys see how I'm going to get the same thing? So this indeed is the correct identity matrix. And then you can extend this to 3 by 3, 4 by 4, 5 by 5. It's just ones across the diagonal. And when you multiply it by any matrix, I get back the exact same thing by the very nature of matrix multiplication. Does that make sense, guys? Does that make sense to everybody or no?
Yes.
Okay. Woo. Woo, woo, woo. Okay. So I tried my best to answer number 4 from the homework while at the same time bringing up the idea of matrix multiplication and how that's related to linear combinations of the columns. So that's my explanation for number I think that was what, number 4. And then number 5 on the homework is something similar, right? So let me just look at number 5 real quick. I'm not going to do it, but it's something similar. This one takes a little bit more. It takes the next step, right? I get 4, -1, 2. And I got A, 1, -1, 1. And I got B, 5, -2, 3. And it's I'm trying to figure out what A and B are, right? I'm trying to figure out what A and B are. So I can rewrite this, of course, right? I can rewrite this as a matrix equation. I can write this as 1, -1, 1, 5, -2, 3. This has 3 rows, 2 columns, and I can multiply this by AB, and this has to give me 4, -1, 2. And I can rewrite this as what? A plus 5B equals 4. I can write this as -A minus 2B equals -1. And I write this as A plus 3B equals to 2. I have 3 equations, but I only have 2 unknowns. So I can use just 2 of these equations and I could figure out what A and B are. Or I can just look at it and see what 2 numbers, when you put them in these equations, give me what I want. And I think that it must be a simple one, right? If I want this to be a 4, what can I make A and B? Like I can make B a 1 and I can make A a -1. That works. You just have to see if that works for this one as well. And it does. So
It does, yeah.
yeah, it does, right? So then this is called an overdetermined system because I have more equations than I need. I only need 2 equations for 2 unknowns. But it just works out. This one works out. Okay. So anything else that you've in the homework that you're like, oh, I don't know exactly, because I think everything else should be okay.
I mean, I think I know it, and I'm getting it wrong with 19, problem 19. But I'm not seeing what I'm doing wrong.
Yeah, the number 19, some people have trouble with. It depends upon like you guys have different matrices, right?
Yeah, but if something has all leading ones, it's an echelon form, and if all leading ones have zeros everywhere else in that column, it's in reduced echelon form. Correct or incorrect? I think that's correct, right?
Reduced echelon form, yes.
Okay, so, but I'm getting it wrong.
For which one? For which one? Do you have the exact the matrix that you're considering or that you're doing?
I mean, there are 4 matrices. There's a lot of,
Oh, this is one of those that all of them have to be right in
yeah.
order for it to be right, and if one of them is wrong, right?
Yeah.
Yeah. Yeah, that RR one, I know not everybody, I think so too. I think the answer, I think 19 is, that's why I was gonna get back to some of these students who had trouble with number 19. Because 19, not all of them have this, but some of them have like the step R to R like this. The problem is they don't specify what the row is. So that's kind of like you have to specify what the row is when you swap. So you can't
No.
just swap. So I think there's a mistake. Personally, I think there's a mistake with that.
That's
Problem.
not it. But that's not it. Problem 19 just gives us 4 matrices.
Yeah, yeah.
A,
Oh,
B, C, and
I was
D.
just looking at, I was just looking at the, pardon me, I was looking at the questions on the chat. And it kept on saying R to R.
Oh,
So
I'm sorry.
no, it's okay. So for those students, right, I'm gonna look into this. But R to R really doesn't make any sense because there's no number to it. Like if you did this and you swap rows 1 and 3, it's one of those things. So I think that's the problem with that.
I
But-
tried like literally all possible combination of row swaps and none of them worked.
Yeah, there's something wrong with that problem actually, I think. That was number 16, right? Yeah, that's number 16.
Yeah.
Yeah. I don't know why it comes out with R to R. There's something wrong with that. Because in my answer key, it says that the first row and the third row are swapped. But that doesn't it's not specified by this. So that's a mistake. That's a mistake on whoever created that particular problem. And I'll take care of that. Don't worry. I may just get rid of that question maybe because it's not right. So 19, right?
Yeah.
So yeah, I guess we can make this the last one, number 19. So can you give me your 4 matrices? I know there's like what? There's only, yeah.
Okay,
The
so
first one?
yeah, the first one is 1003.
Oh,
0.
okay. Hold on. 1003, and then
Then the next one, the next row is 010 -2.
that's it.
And there's a 0 row.
And there's a 0 row. Okay. So what kind of
Reduced row echelon form.
yeah, this should be reduced. Yeah. This is definitely reduced. Why? Because I have the ones here and I have zeros everywhere else, and the bottom row is all zeros. So that's true.
Okay.
That's the
So
first one. Okay, next one.
next one is -4
-4.
0 1.
Uh-huh.
Row 2 is 0 -6 0. And
Okay.
that's in neither because there's no leading ones.
There's no leading ones. Right. So then you say
Not
yeah,
an echelon form at all.
right. Well, it's not it. Let me see. This one I think is.
But it has no leading ones.
Not an echelon form, yeah. This is 4 0 -6. Yeah, not an echelon form. Right. This is neither. Or not at all.
Yeah,
Okay.
there's just the 3 choices.
Mm-hmm.
Okay,
Then
and
the
then
next one? What's the next
next,
one?
okay, the next one has 4 rows,
Okay.
and row 1 is 5 -2
Mm-hmm.
3 -6 -4.
Oh wow, that's 5 columns. Okay.
Next row is 0 -10, and the
Yeah.
rest is ones.
Okay.
Row 3 is 0 0 1 0 4,
Uh-huh.
and one more is 3 zeros, then a 1 and a 0.
Okay.
And I said that this is not an echelon form because I don't have all leading ones.
But you have some leading ones, right?
Right, but that's not an echelon form. Echelon form requires all of the rows to have a leading one.
Not necessarily. Doesn't have to have all leading ones. Because if it's all leading ones, then it would be in row echelon form.
No,
I
it
think-
would be in row echelon form if it's all leading ones and zeros everywhere else.
No,
I
no,
mean,
no, 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 no. So I think that's okay. So there's a difference between just echelon form, and I think what they're using echelon form is to be row echelon form. So there's something up with this homework, and I realize. So there should be, I'm assuming they're using this row echelon form. So then if that's the case, then you're right. You're right that this is not an echelon form, meaning this is not row echelon form because you don't have ones all along the diagonal. That's you're right about that. If you have zeros, if you have all ones in the pivots, right? If you have pivots and they're all leading ones, and you have zeros above and below, then you have what's called row reduced echelon form. And I think what's happening is that they don't put the word row in it. They just write echelon form and reduced echelon form. But they should write it as row echelon form and row reduced echelon form.
or
I don't
maybe
know.
that's why I'm getting it wrong because
Yeah.
I'm doing it to row and they're not.
The thing is, there's such a thing as echelon form, where echelon form is a bit more liberal with the idea of the leading ones. Echelon form is you have this kind of triangular shape, right? So this would be, for example, this would be an echelon form, but it's not row echelon form, meaning that it doesn't have ones in the diagonal. I know it's just like semantics at this point. It's not like a big difference. But then,
Professor,
yes.
Yeah, so for the echelon form, so the leading entry doesn't have to be 1, right? It can be any number.
Okay.
Yeah,
If
like
it-
for example, the B like -401, the leading entry is -4, but below -4 is 0, so it can be echelon form, right? Or it has to be leading 1, the leading entry, or any number is okay. Like -4 is okay for the leading entry.
okay. So I just want to make, there is a distinction, okay, between echelon form versus row echelon form versus row reduced echelon form. There is a difference. For row reduced echelon form, I believe everybody, so this is just REF, right? This is REF, and this is EF. I don't know why this problem required to, usually we don't use echelon form, but we usually only use these two. But row reduced echelon form, we know, we get it, right? We have ones and we have zeros above the ones and 0 below the ones. That's clear, correct? In row echelon form, REF, we have all the pivots are ones. But the numbers above those ones, the leading ones, are not necessarily 0. So I should say this. So zeros are above and below leading ones. The zeros are only below leading ones. And echelon form is not even like, can you draw a simple example? Yeah, I don't think a 2x2 is enough. I think a 3x3 would be better. So yeah, I was gonna use an example for this. So like, if I had something like this, right? If I had one, let me see. If I had one, sorry, 0, 0, right? 2, 0, 4, something like this. And I had 1, 2, 3, and 0, 0, 0. If I have this, this is what? This is REF. Why is it REF? Because I have leading ones. I only have 2 of them, but I have leading ones. And the number above one of the leading ones is not 0. So this is REF form. What would be the RREF form? So this would be 1, 0, 0. This would be 1, 0, 0, 2. If I do -2, this would be -4. This is 0. And then -2 is, so this would be -2 like this. This is RREF. Why is that? Because I have leading ones here, but the numbers above and below are all zeros. So I think we understand the distinction between REF and RREF. This is row echelon form, and this is row reduced echelon form. Now, what in the world is echelon form? Echelon form looks like what we just had here. Let's say I do this. I do 8, 4, 0, 8, 0, 1, 2, 3, 0, 0, 0, 0. This is echelon form.
Is that because there is a leading one in any of the rows, or is it because
It doesn't have to have a leading one. So I could do something like this. Let me do this. Let me do 2, 4, 6.
according to equation B that we did before, according to this equation B that we did before, should be an echelon form?
I agree. I agree. That's why I agree. It's just that I also misinterpreted because it's not clear, right? Because I assumed, that's why I put the parentheses. I assumed that they meant to say row echelon form, because echelon form, just echelon form, is not really spoken of. We don't really like. But echelon form is in the form where you have a diagonal being created, right? You have this diagonal being created. So echelon form is just simply a matrix in the process of becoming row echelon form.
So would echelon form be defined as there are zeros below all the leading numbers?
Yes.
Okay, and so oh, because then I have the last matrix is 1 1 -10 and 1 0 -6, and that would be not an echelon form at all, even though it should be in row, even though this is in row echelon form.
What do you say? 1 1 -10 and
1 0 -6.
right. This is not in any form.
Shouldn't it be in row echelon form?
It's not in row echelon form.
But I have leading ones.
You have a leading one, but remember what we said, row echelon form says we have zeros below the leading ones. There's no, if this is a leading one and you have a one underneath it,
Right.
how is it row echelon form? So you would have to make this a 0 and then you have row echelon form, because then immediately that's all you have. You only have one leading one that has an entry below it, because this number here would be whatever this number would be. So look, this is not in echelon form. Okay.
Yeah.
I do one more step to it. I do one more step to it to make it into echelon form. I negate this, right? And I add it to row 2 and I get 1 1 -10. I get 0, right? This becomes -1. This becomes what? 4. What is this? Echelon form. It's not row reduced. It's not row echelon form. Why? Because I have a -1. How do I make it row reduced echelon form? I just negate the second row, right? This becomes 1 1 -10. This is 0 1 -4. This is in what? Row
Row echelon form,
echelon form.
but not in reduced row echelon form.
It's not in reduced row echelon form because
because
the leading ones are there. I got the leading ones, but I have this one on top of the one, the second leading one.
Yeah, I just put it into the thing and I got it correct this time. So
okay, yeah, I know. It's I personally apologize for that because I didn't realize that they meant echelon form. I assume it's row echelon form because echelon form, we don't really talk about echelon form like that.
yeah,
But
I
now
don't
you
think
see the
the
distinction.
textbook mentions it.
Huh?
I don't even think the textbook.
Yeah, the textbook doesn't even mention it. Exactly. It's one of those like it's just before, it's right before being, it's like a caterpillar, and then you have a larva stage, and then you have like the butterfly. You know what I mean? Like it's like that kind of stage. So this is the stage right before he gets into the larva stage, which is REF, and then becomes a beautiful butterfly in RREF. You can think of it that way. I don't know. And this becomes what? -6, right? -4, and this is in row reduced echelon form. So it's just the semantics here. For some reason, they just jump from echelon form to reduce echelon form. They don't even speak about row echelon form, which is important. This is more important than this. This here, these two things are more important.
Thank you.
Does that make sense?
Can I mention another matrix just to like make sure?
Yeah.
So like 1 0 0 8
1 0 0 8
0 0 0 0
0 0 0 0
and then 0 1 0 -2.
0 1 0 -2. What do you think?
So that would be like reduced row echelon form, right?
That's not echelon form anymore, is it? Because if there's a row 0,
Yeah, so that's one extra little thing. So this is one of those like weird cases, right? It's not anything. It's almost there. Why is it almost there, and why is it not anything yet?
Can't you like switch it?
Yeah, you have to switch it. You have to switch the second, the third row, and then you automatically got it in row reduced echelon form. So previous to that step, this is nothing. This is not in any form. So
Okay, I see.
the placement of the ones matter. Despite the fact you have just ones randomly, right? The placement of the ones do matter. The pivots occur in the diagonal starting from this diagonal here, right? That's where the pivots should occur. It doesn't always occur, but it should occur. The moment you miss this out here, you miss it. It's not a row reduced echelon form, row echelon form, or an echelon form. And so, yes, so I think that's one of the questions here. Also, jamming had the same thing. If you have zeros in between two pivots, right, it's no longer an echelon form. It is no longer an echelon form. So the echelon form has this necessary part of it where it's like a triangular shape, right? It's like there's like a triangular shape to it, a diagonal that has to kind of be kept. If it's not, then it's not an echelon form. Wow. Now I think, this idea of echelon form, row reduced echelon form is clear as day. So you see, this is why it's good to do these problems, because now you've tackled this topic through and through. You're like, okay, now I really know exactly why this is true, why this is not true, why it is row reduced echelon form, why it isn't. So any questions about this stuff? Any more questions? What if the bottom row doesn't have a, okay, see, now you guys are now you guys are coming up with some good stuff. Okay, so if you have 1008, right? We got 0000, and we got 000 -2. So now you're giving me a brand new spanking matrix. What is what would you guys say this is? Matrix is in what form?
Reduced row echelon form. No, because it's not not all non-zero lines, right?
So first of all, that row of zeros in any echelon form would always have to be in the bottom. So this is not in any form. So how do we make it into a form, an echelon form? We just have to swap the second row with the third row. So you get this. So this is not any, right? Not any form. And what is the one to my right? What kind of form is this in?
It's also in no form at all.
Maybe
Maybe an echelon form.
it's an echelon form. And then let me do one more thing. Let me make that -2 a 1. So I divide by -2, right? And then this is what I get. What is this? This is not RREF.
Row echelon?
It's row echelon form.
Okay.
Why? 1 leading 1 leading 1. And what happens above the leading 1? Hey, I have an 8 above one of them. So it's not row reduced echelon form. It's right before it. And then when you get rid of that 8, this is my row reduced echelon form. So I don't know if this is even clearer now as to how you go from having a matrix that has in no form to echelon form to row echelon form to row reduced echelon form. You see, I have leading ones here. The leading ones never occurred in the second column nor in the third column. It occurred in the fourth column because of this number here. It was in the fourth column. I didn't have anything in between. So there's no a possibility of having a leading 1 here. There's no way. because there are no numbers to make it. Do you guys see that? Any questions now about about echelon form? Where we do echelon form?
Can you go back to number 5?
Number 5 for what?
The Weber number 5. I want to see the final answer.
The final answer is just figuring out what A and B are. I know your numbers might be different, like these numbers here might be different, but they're asking you, what should I plug in for A and B so that when I perform this operation, I get exactly the thing on the left side. Yeah, the numbers are going to be different. So in my version, I have these are my numbers here, right? So then what I did here was just I just wanted to show you guys what this means and something that we've seen before, right? This is the linear combination version of a matrix equation. So these are my columns of my matrix. My matrix is the first column here and my second column here. And I'm multiplying this by the matrix, the 2x1 matrix AB. And when I perform this, I get this column vector. Another way you could think of it, another way you could have thought of this is you multiply everything in here by A. So what happens? I can think of it this way. What happens if I multiply, because this is a scalar multiplication. A is a scalar, and I'm multiplying it to a vector. Remember what we do when we multiply by scalar to a vector? We multiply every entry by that scalar. So this is what I get when I think of it this way. I have my vector A negative A, and A. That's all I did. I multiplied every number by A. And I'm gonna do the same exact thing for this thing here. I get what? I get 5B. I get negative 2B, and I get 3B. Now I have a matrix 3x1, which is a column vector, and I have another matrix 3x1, a column vector, and I'm adding two things together. They're the same size, which is good. If I add the same thing, what do I get? A plus 5B. Negative A minus 2B. A plus 3B. That's the result. So then I went from here to here to here. And I'm saying that this guy is equal to this guy is equal to this guy, which is equal to this guy. So that means that this guy must equal 4, negative 1, 2. But if I tell you that this matrix, which is 3x1, equals another matrix, which is 3x1, or a column vector equals a column vector, the only thing I can say now is that this first row has to equal this first entry here. So that's why I can rewrite this as A plus 5B must equal 4. Negative A minus 2B must equal negative 1, and A plus 3B equals 2. I have a system of equations, 3 equations with 2 unknowns. It could be that there is no solution, or it could be that there is. And it just so happens that there is, because if I were to solve it, right? If I solve this system here, just using 2 equations with 2 unknowns, because I only have 2 unknowns. If I solve for B, for example, how do I solve for B? I can add the 2 equations, right? When I add the 2 equations, what do I get? The A's cancel, right? I'm doing elimination here. And this becomes what? 3B equals 3, so B equals 1. I got one solution. If B equals 1, then what is A gonna equal? If this equals 1, solve for A. 5 times 1 is 5. A is equal to negative 1. And just in case, to make sure it works, you would have to plug in, right? This is negative 1, this is 1. This is negative 1, this is 1. They work out. And this is negative 1 plus 3 times 1. Well, this is 1 minus, this is negative 1 plus 3, which is 2. So my solution is A equals negative 1 and B equals 1. Of course, your numbers will be different, but it's the same idea. Does that make sense? And then number 16, yeah, number 16, that I think I may just cancel out 16 because it's inherently the one that I have. Yeah, it's not correct. There's a flaw. It's a faulty question. It's one of those just randomly faulty questions. Okay. But besides that, I think everything else should be okay. I think we covered everything. Matrix multiplication, of course. So, all right. So hold on before you guys go. I'm gonna stop the recording here. We're done.